as our third keynote speaker. She is one of the leading econometricians of our times. She has substantially advanced bootstrap methods in econometrics and statistics as well, and with seminal contributions in time series, in macroeconometrics, in panel data, and in financial econometrics. And I don't think many econometricians can claim contributions in all of these areas, which each of them are very big. Silvia did her PhD in UCLA and is currently full professor at McGill University in Canada. She has published many important contributions and papers in top economics and statistics journals such as Econometrica, Journal of the American Statistical Associations, Journal of Econometrics, Journal of Business and Economic Statistics, just to name a few. She is also currently the associate editor of Journal of Econometrics and of the Journal of Business and Economic Statistics. She received several awards for her papers, and something I didn't realize it existed, also a prize for the best associate editor of Journal of Econometrics in 2019. Another thing maybe that's important to know for people both interested in applied and theoretical econometrics, is that her papers are exceptionally clearly written, no clutter notation, no extra things, to the point that if you're looking for a method and you're just an applied person, you will be able to understand what this method is from her paper and apply it. And if you actually want to learn how to prove bootstrap validity, you can just go to our appendixes. And the reason I'm saying this is because that's how I learned to prove bootstrap validity. I did not go to a book or some other online source. I just went to her paper with Lutz Kilian, read the proofs, and it was clear to me how to prove bootstrap validity. So it's an honor to have Silvia here. And she will present about out-of-sample predictability tests with real-time data.
Well, thank you. Thank you so much for having me here, and thanks for such a great introduction. You set the bar really high now because I'm feeling a lot of pressure. The notation in this paper is quite complicated, but hopefully you'll get the main idea. So this is actually what I'm going to show you today is a joint work with Mike McCracken, who's a specialist on out-of-sample predictability testing, and a student of mine at McGill, Kai Yao. So what is the main idea? What we do in this paper is look at bootstrap methods and more generally inference methods for testing out-of-sample predictability when there's real-time data. So as we know, prediction and forecasting is a real-time exercise. Central banks use these methods to forecast all the time, and what they're going to use is the most current data that they have available. And that data typically is subject to data revisions. So in the methodology section of these papers, or in the exercises that central banks conduct, they will typically want to forecast, to evaluate their forecasts. And so there's a lot of ways of testing for predictability out of sample, starting with Diebold and Mariano and West in the 90s. But most of these tests rule out data revisions. So they will just use the fully revised data for their out-of-sample tests. And one exception to this literature is this earlier work by Todd Clark and Mike McCracken in the JBS. What they pointed out was that if you allow for the possibility that the data that is being used to testing out-of-sample predictability, then the distributions that were derived under no such data revisions will change. And so if you don't account for those changes, you end up with size distortions that you could avoid if you allowed for data revisions. And so that's how I enter in this research project. Talking to Mike, who was a previous co-author of mine in different projects, the idea was, can we develop bootstrap methods that can be used in this context and that will be robust to data revisions? For those of you who don't know, out-of-sample tests are typically sample averages of testing functions that depend on target variables and predictors, which are subject to revisions in this context. And so, to the extent that these are averages, you need to account for the dependence in these averages, and the question is, how do we use the bootstrap in this context? It's been used before without data revisions because, as you'll see throughout the talk, when you're testing for the null that an expectation is 0 and use the sample average, that average will be asymptotically normal under the null, but the variance can be quite complicated in this particular testing problem, and the reason is that when you compute these averages, which are your test statistic, the average depends on some parameter that was estimated first. And so if you want to account for the parameter estimation uncertainty, as you should, because you've produced your forecasts using models that you first estimated, well, then you need to compute quite complicated variances. And that's why the bootstrap is useful in this context, and it has been proposed exactly to avoid having to explicitly account for these complicated variances. And, as someone who has worked on the bootstrap, this problem interested me very much because I had read this literature without data revisions, and the question was, what would change if I wanted to compute the distribution of such tests allowing for data revisions? And so what I'm going to show you today is the result of 2 papers that we've written so far on this topic, and the general goal will be to propose methods that can be used with data revisions, and in particular, we're trying to target 2 types of revisions that often appear in macro data. Those are the so-called regular revisions and also the benchmark revisions. So let me, if you're like me and didn't know about the data structure underlying this problem, maybe the next table will give you a better idea of what I mean here. So here I have a table with vintages for non-farm payroll employment. These are monthly data. So in each column, you have a so-called vintage of data. That would be the data that you have available for that month. And then I have different columns which correspond to different vintages. So you can think about each vintage as being the data that is the most recently available data for the person who's forecasting. What you see in the table is that I've highlighted in colors the 2 last observations in each column. Those are highlighted because they're not fully or final data. They're going to be subject to revisions. In particular, the very last observation in orange is what's usually called as the advanced estimate. That's the first released value by the statistical agency. That first released value is preliminary and is going to be revised the next month. And in yellow, that's the second revisions or release. So you can think about this as the first value that was released by the statistical agency, which gets updated in the next vintage. And each month you have these 2 preliminary or first 2 releases of each data. In this table, everything that is not highlighted is considered to be fully revised or final. In reality, the table that I have here does not quite correspond to what you would observe in practice, because for these particular data, you would have a further round of revision, which occurs once a year, and those are the so-called annual benchmark revisions. For most of my talk today, I'm going to ignore those. I'm going to describe a bootstrap method that allows me to capture these different vintages without accounting for this extra round of revisions. And the reason is essentially simplicity. It's going to be already quite complicated to bootstrap this data. We have a second paper going on right now where we allow for these annual benchmark revisions. So annual benchmark revisions would look like this. So imagine that in this particular month, you have a first release that gets updated the next month, and then that value is not quite final up to February, when all the data that was preliminary up to that point gets fully revised. So you see that in blue, I have the data that corresponds to the second released data, which is awaiting for a final round of revisions, if you want. And so what this shows is that the blue observations here are not fully observed. They're not, well, they are observed, but they're not final, essentially. And so, as I said, we're going to want to bootstrap this data with the aim of replicating the asymptotic distribution of our test statistic. And because the annual benchmark revisions really complicate the problem, we started with this simpler problem where we ignored those. But turns out that we have some positive results about the annual revisions, and I'll explain at the end what changes, okay? In a nutshell, before I get into the details, as you know, the bootstrap is a statistical method that aims at using simulations to obtain critical values for tests in this context. And typically the principle of bootstrapping is that one should try and mimic as closely as possible the dependence and heterogeneity structure of the data. So what does this mean here? Well, you see that you have different columns of data. Each corresponds to a particular vintage. These are time series, so you should expect some dependence, some time series dependence within columns. And so the bootstrap should replicate that. And for that, we're going to use a moving blocks bootstrap, which is a particular method that allows for dependence. But then more importantly, you see that these numbers, they repeat themselves across vintages. I mean, these are not new data. They're either the same data that is already fully revised, or they're updates of preliminary data. So we will want to mimic the dependence across columns. And the way we're going to do that is by drawing a set of random indices with which we're going to reshuffle our data, and then we will want to use those indices to populate all the other columns. That's essentially the idea. Now, as I told you in the introduction, we're not the first to propose the bootstrap in this out-of-sample predictability testing framework. There are papers, in particular by Valentina Corradi and co-authors, who have looked at this problem, but they have ignored data revisions. And so what does this mean? It means that what they essentially do is they conduct their tests using the final column here, for which all the observations except the very last two are preliminary. So clearly, the bootstrap methods that they propose bootstrap only this column. But what we need is actually, we need the bootstrap to replicate these tables somehow. And so that's just to explain why is there a need for new bootstrap methods. Now, today's talk, as I said, is based on two papers. The first paper, which is forthcoming in the Journal of Econometrics, was the first paper that proposed the bootstrap in this context, allowing for data revisions. It essentially used the framework of Clark and McCracken 2009, but applied the bootstrap instead of their asymptotic inference methods. And as them, we assumed only regular revisions. So think about the first table. More recently, we started working on a second paper, which relates to the first, but the aim here is to actually allow this more realistic framework where, in addition to those regular revisions, you also have these once-a-year revisions. And as I've shown you in the table, that complicates substantially the structure of the data. And a bit to our surprise, we have actually two positive results. First is that if you don't want to use the bootstrap because you think it's too complicated and you're fine with using the normal critical values along with the covariance estimator, well, it turns out that the method by Clark and McCracken in 2009, which ruled out annual revisions, is actually fine. We started out showing it in simulations, and you know, at first I was like, how could this be? You're right. I mean, they have not allowed for regular annual revisions. How could their estimators of the variance still be okay? And we now have an explanation for that, and I'll hope to get to the end and explain intuitively why is that the methods that they proposed under more stringent conditions end up being robust to annual revisions. Now, given that positive result, the second one, which I have in the slide, follows naturally, and that is the robustness of our bootstrap method, which I'll explain to you next, to those annual revisions as well. That's easy to understand in the sense that that method is going to do what Clark and McCracken do in their paper without the bootstrap. So if their method works, ours will also work. Okay. So given that, let me start with the first paper where we're only allowing for regular revisions, and this is where I, contrary to Ottilia's claim, maybe my notation will become very quickly complicated, and I apologize for that, but I'll try my best. So let us think about the typical framework in this literature, which is you're someone who's trying to test, for instance, you have a model, you use that model to produce a forecast. Maybe you care about testing whether the forecast is unbiased. So you have in mind a null hypothesis where the null says that the expected value of the error that you get from that model is 0. How do you do the testing problem? Well, what you typically do is you're going to do a pseudo out of sample exercise. What this means is, imagine you have capital T observations, you're going to split your sample in two parts, one that runs from 1 to capital R. You use that sample to estimate your model, because you're producing forecasts with models that you estimate. And then you're going to, say you're doing a one step ahead forecast, well, you're going to produce a forecast for the one step ahead using that estimated model. And that gives you, because this is a post exercise, you know what the value is of yt plus 1, you can contrast that with the forecast you got. And then you repeat this exercise. You augment the sample, so you go from 1 to R plus 1, estimate the model again, produce another forecast, now for yt plus 2, you get an extra forecast error. So by recursively generating forecasts in this manner, you'll end up with a certain number of predictions. Those are out of sample predictions because you pretended that you were a real forecaster which only observed observations 1 to R and then produce a forecast for the next period, right? So we're simulating that, and what this means is that at the end of the day, we're going to have a set of P predictions that start at time capital R. That's your first forecast origin, and you go on this way up to the last point. And so you're trying to forecast a target variable y using a set of predictors x. Now, because we're trying to do forecasting using real-time data, using those vintages of data, I'm going to use the predictors and the y's, they'll be from those columns that I showed you. So we have then this bracket notation to indicate the vintage. So think about, you're sitting at time t, little t, you're trying to produce a forecast at time r plus 1, you're going to use your vintage from that time t. And that data is this column data, okay? We're going to assume, in addition, that as in my tables, there's only a finite number of data that is subject to revisions. So I'm going to call little r the number of releases, and that's assumed fixed. It's not going to diverge. So there's a finite number, little r, of releases for a total of r minus 1 revisions, okay? So just to set the notation, suppose that you were facing a situation where there's only one revision. What this means is there's two releases of the data, one that is preliminary, which gets updated to final in the next period. And so what that corresponds to in terms of my notation is that the vintage t here will have most observations, all of them up to time t, as final, so there's no bracket notation here. And then this notation here corresponds to the first release of that observation. And since I'm assuming that there's only one observation which is preliminary, well, there's only one such release, okay? So that guy will get updated to YS in the next vintage. So what this leads to is, again, a triangle array structure, similar to what I showed you for that data that I had in the beginning, but now simplified to having only one preliminary observation, which amounts to the very last observation in each vintage, in each column, okay? And keep in mind that what we're trying to do here is to come up with a bootstrap that replicates this structure, okay? So we would like the bootstrap to actually identify the very last observation in each column as being final, as being preliminary, and everything else as final. In terms of the framework, what we're going to do, as I said, is we're going to use models that we estimate with OLS to forecast the target variable. When you are dealing with real-time data, depending on your objective, you may be interested in forecasting a final value or a preliminary value. We're agnostic about this in the sense that we allow for any of those. And so in terms of notation, I'm going to call, if I'm looking at the tau step ahead forecast of y, then the target variable is going to be the r prime release of that value, where r prime is, again, something you decide, and it could be any number between 1 to little r. If it's little r, then that's the final value. You're interested in forecasting the final value of your target variable. If it's anything else, you're forecasting preliminary releases, okay? How do we construct forecasts? Well, linear models. We're simplifying. I mean, in this literature, you don't have to estimate and forecast using linear models, but those are, in practice, what people tend to use, and this is our focus here. As I explained to you before, typically, again, in a real-time exercise, you would forecast using the data available at time t, you'd forecast out of sample. And then you repeat the exercise recursively. And so that's what this estimator beta hat t here is. This is just the OLS formula, x prime x inverse x prime y, but expressed in terms of vintage t data, hence the parentheses in the notation. Okay, so this is a real-time OLS estimator. It's recursive because as you increase t, you're expanding the window that you're using to estimate beta. Right? And then once you get this estimator, your forecast for y, t plus tau, is the linear combination of the predictors that you decide according to your model times beta hat t. And those predictors here, they're actually most of the time preliminary, right? They are the final data in that vintage. Typically, you're predicting with AR models. If you think about those would be the last observations in vitro. So the predictors are typically preliminary. This beta hat t can be computed using the preliminary data or the final data. Why is that? Well, asymptotically, because I've assumed that there's only a finite number of preliminary observations, and I'm going to let the sample size increase, you know, I could estimate this object using the vintage t data or alternatively using the final data. You know, if you have an infinite number of data, having a few ones that are observations that are preliminary won't change the estimator, okay? What is the null of interest that we care about here? It's something that looks like this. So you have a testing function f. That's something you decide. That's your loss function. You want to compare forecasts using a certain loss function, you're going to choose f. This f depends on the target variable and the predictors, and both can be preliminary, as well as some parameter beta 0, which will be the limit in probability of the OLS estimator. Okay, so what are examples of this function f? I've alluded to before testing for unbiasedness of your forecasts. Well, that would amount to an f that looks like this. This is the forecast error. We're trying to forecast y using these particular predictors. Well, we want to test that the null of this function is 0. Another more popular choice is when you're using these tests to test the predictability of different predictors. So say that you're trying to forecast y at time t plus tau, but you have two different sets of predictors, and you ask yourself, are these predictors equal in the MSE, in the mean square error sense, out of sample? Well, then the function f would be the difference of the squared errors, and what you want to do is test whether in this population the two are equivalent. What are the statistics? Well, the statistics are going to be the sample averages that correspond to this null, right? So we're testing the null that the expectation of some function f is 0. It's natural that we're going to use the sample average. The sample average is going to be constructed in the out-of-sample period. So you see that what I have here is the sum starting at the forecast origin r, going all the way to t, scaled by the square root of the number of predictions, which is p, of the function f. F is known, you choose that, and the only thing that we do is change beta 0 into some estimator. That could be the real-time estimator or this guy here, the final OLS estimator. As I said, actually it turns out that the first result we prove in the paper is that using the final estimator based on the fully revised data asymptotically is the same as using the real-time OLS estimator. Why? Well, the reason is that you're using those columns of data at each point in time to forecast your model, your variable. You're using OLS. Only a few number of observations in each column is preliminary. If you were to use the very last column where all those data are final, you'd get beta hat t without the parentheses. Well, that would be asymptotically equivalent because there's only a finite number of points that will be different, essentially. And so the reason why we introduced this new statistic, which is based on the final OLS estimator rather than the real-time OLS estimator, is because the theory for the bootstrap is actually much easier to derive for S tilde than for S hat. Okay. Now, what are the assumptions that we use? And this is kind of important to understand the final part of the presentation. So in the paper that we first wrote, which is forthcoming in the Journal of Econometrics, what we did was use essentially the framework of Clark and McCracken, 2009. And so what they did was extend this famous paper by West in Econometrica to allow for regular revisions. And so our assumptions will be similar to those. And essentially, what we do is impose some continuity and differentiability assumptions on this testing function f. That's, again, typically people think about MSE criterion to compare models, so that would be satisfied. And then what we do is we impose some moment and stationarity and weak dependence assumptions on this vector G. What does this vector contain? It contains several elements. One is the testing function, which depends on preliminary data. That testing function depends on preliminary data because it's a function of the target variable, which, as I said, could be preliminary, and the predictors, which most surely will be preliminary, since they correspond to the last points in each vintage. So we include that in our function, in our vector G. And then we include the gradient of that function vectorized. So this is the derivative of f with respect to beta. As well as h and x. X are the regressors, and H are just the score. This is X times the error term. That's the score underlying this OLS problem. And so what I'm saying here is that we assume this vector to be stationary and mixing, so some sort of dependence that decays with time lags. This is important. The stationarity assumption is typically a maintained assumption in this literature. If we're imposing it here in this vector, it's important to realize that this assumption later on, when I talk about annual revisions, this assumption will not be a good assumption. But under regular revisions only, this is okay. So we assume this process, whatever enters these different elements, they're stationary over time and they're well behaved so that we can apply central limit theorems. Then, as I told you, we're assuming that R, the number of releases, is finite, and that's actually a crucial assumption in all I'm saying. And we're imposing some existence of moments for the data, including the revisions. And finally, the last assumption here describes the asymptotic framework. So remember that we've splitted our sample into an in-sample period with capital R observations, and then the out-of-sample period has capital P observations. We're saying that both are expanding at a certain rate so that the ratio is this little pi. This is not something new to us. This comes from West 96. And essentially this little pi here matters because if pi is 0, then you're saying that your OLS estimator based on R has a lot more observations than the number of predictions. So essentially what this means is that you don't have to worry about parameter estimation uncertainty. But when pi is not 0, then you should account for parameter estimation uncertainty. So this slide here is a summary of the asymptotic theory. Unfortunately, I have to give you this slide so that you understand later on the idea of the bootstrap algorithm. Without this slide, I won't be able to explain it. So just bear with me for a second. But essentially, what does this say? Well, we have a statistic, which is an average. That's the S hat. We're subtracting the mean. That mean will be 0 under the null, but under the alternative, it will be something else. And what we're doing here is decomposing this average into a bunch of terms. The first term here, this is an average that I'm going to call S1. This is an average of what? Well, it's an average of the testing function centered around its mean. That testing function depends on preliminary data. So that testing function is affected by data revisions. If I evaluated that function on fully observed data, I would get a different variance than if I evaluated on preliminary data. So that piece here, S1, converges to a normal distribution centered at 0, because these guys are centered, with a certain variance omega 1. That's part of the overall variance. Okay? Then the second piece here is what captures the estimation uncertainty of the beta. If I knew beta, this guy here would drop out. It's because I don't know beta and I need to estimate it at each point in time that I have this extra piece. That extra piece depends on capital F, which is the expectation of the gradient or the derivative of the little testing function f with respect to beta. So if this derivative is 0, well, essentially that means that estimating beta has no impact on the distribution, so it drops out. But in general, that's not 0. And then what you have here, more importantly, is a second average. It's an average of complicated terms that depend on the score function, and those capture the estimation uncertainty of the beta. So I'm going to refer to that as S2, and what West showed was that this term 2 satisfied the central limit theorem, so it converges to a normal centered at 0 with a certain variance omega 2. And so when you put everything together, the asymptotic distribution of the overall statistic is normal, centered at 0, with a complicated covariance matrix, which is this. This is exactly what we're trying to avoid to estimate explicitly by using the bootstrap. We don't want to estimate this. But if you're not going to use the bootstrap, then you need to have plug-in estimators for each of the components in omega in order to proceed. So what I've highlighted in red are the pieces that are affected by data revisions. So if you compare this work with West, where there was no data revisions involved, the only thing that changed were the pieces in red. And it's easy to see that these pieces in red, they are affected by data revisions exactly because they are the pieces that depend on the testing function. And the testing function depends on the preliminary data. If I observe that data fully, that I'm going to get a different variance, okay? So that's how it matters for us. So what this slide says is, I have a well-behaved limiting distribution. I could not use the bootstrap, but then I would need to estimate this complicated variance. Where I will enter is, what kind of bootstrap scheme would replicate this? Can I devise a bootstrap algorithm that captures these different components implicitly and allows me to use critical values, not based on the normal distribution, but based on a certain bootstrap distribution. And so the question really, as in any application of the bootstrap, is what kind of bootstrap method should we use? And that's why, I've covered over time a lot of different methods, exactly because every time there's a new problem at hand, a new bootstrap will apply. Okay? And so this is the question. So let me skip this part. Let me go straight to the tables because I think it's the easiest to understand. Now, let's go back to this very simple example where there's only one revision. So there's only one final data, one preliminary observation at each end of each vintage. What I want is to replicate this structure in the bootstrap world. So in particular, and remember, there's different criterions here. It's not any bootstrap. What this bootstrap should do is, it should allow for dependence within each column. Because these are time series, there's going to be serial correlation. I cannot do an IID bootstrap. I should do something more sophisticated. What we're going to do is a moving blocks bootstrap. We're partitioning our data into blocks and then resampling blocks because that's well known to mimic dependence. So we're not innovative in that way because we're using just a dependent block bootstrap for this. So we want to use the block bootstrap to get our bootstrap observations for each column. But then, as I told you, we cannot just apply the block bootstrap for each column independently. Then the columns would be independent in the bootstrap world, whereas they are not in the real data, right? These data are the same as these ones, Most of the data, only the ones that get updated change. So clearly, what we need to reshuffle the data using some set of indices that will be the same across columns. That's the second criterion. The third criterion is that we would like the final observations in each column to be preliminary, since those enter the testing function. And if I generate a bootstrap and I replace this orange by something that is final, then certainly I'm not mimicking that characteristic. And this last criterion is what is really important here, is that if you take the existing methods by Valentina and Norm and others, what they would do is they do a block bootstrap over the whole observations. So they generate a set of random indices with which they were going to reshuffle the original data, and they're using a block bootstrap for that. But essentially what they do is generate those indices from the whole set of numbers starting at 1 going up to t, right? Why wouldn't that be applicable here? Well, suppose that you're trying to reshuffle this column here, right? So you know that you need to set the observation R+1 as preliminary. But you also know that that observation gets to be final in the next month. So if I were to reshuffle, if I'm going to draw a random index that will be the bootstrap equivalent of these, from the whole set of numbers, I could draw, for instance, observation 2 as a replacement for this observation.
But if I do that, if I draw 2 as my random index for row R+1, then I won't have a preliminary observation for observation 2. Because in my data set, observation 2 is fully revised. I don't have access to its preliminary version. So that led us to consider the following alternative, which is split the data into 2 parts. So if you notice, the first part of the data is mostly final. That part of the data ends at the forecast origin capital R, and it's really mostly final. There's only this guy in orange. Whereas the second part of the table is the triangle block here, which has that regular structure. And so what we did was the following. We're going to use a first block bootstrap in the first part of the table, which means I'm going to draw a certain random set of indices, but my random indices are going to be drawn from numbers from observations 1 to capital R. So I'm going to restrict the support of those random indices to 1 to capital R, because for those indices, I only have final data. And I'm going to set that block all as final, which is fine, except for the first observation. And then the second block here, which is the triangle, I'm going to draw a new set of indices, also using the block bootstrap, and this time those set of indices are going to be living in this set, R+1 onwards. So I'm going to randomly draw from numbers R+1 onwards, because for those, I am sure that I have both a preliminary observation and a final value, right? After all, in the real data set, for R+1, I have a preliminary, and then I know it's final. For R+2, the same. So by doing this application of the moving blocks bootstrap twice, I'm able to, at the same time, preserve dependence within each column, which is important, and at the same time, I'm able to enforce the classification of the observations in the second part of the sample as preliminary along the main diagonal and final of the diagonal. That's essentially the idea. Now, I didn't, can I ask how much time do I have?
10 minutes.
Oh, okay, so I'm glad I didn't give you the details, but essentially one could wonder, does the fact that I, generate 2 sets of indices independently matter? After all, in the real data set, this part is not going to be independent of this part, but in the bootstrap world it will be. So is this a problem? Turns out that it's not a problem, and that's something that has to do with the asymptotics that I didn't describe, and I won't have time to describe. So this is the table that actually says exactly what I said in words, so let's keep that. And this is the bootstrap algorithm. Let me just go to the final part of the paper, which is the second paper that we are currently working on. So if you remember, in this second paper, the main question is, what if we have annual revisions? After all, the data structures we see in practice are not as simple as I described them up to now. Well, the main impact of annual revisions has to do with the stationarity assumption that I made before on this vector G. I'm going to try to convince you that if we allow for annual revisions, such an assumption is not a good assumption. And therefore, we need to revisit the theory, both from the asymptotic viewpoint and the bootstrap viewpoint. And the positive news is, or the good news is that even though the assumptions will change, the methods will still be valid. So that was actually quite new, quite good news, and even Mike McCracken, who's a specialist in this area, did not expect it. So we were very excited about this result. Okay, so let's see again intuitively why would this matter. So I'd like to ask your attention for the following. Suppose this table looks much more complicated. So think about now, imagine that you have quarterly data, and once a year, there's going to be an annual revision, okay? So that's why I've split this table into columns of 4. So imagine that the first column is a period or a quarter where there's an annual revision. That means that all the data that could have been preliminary before got to be final, so there's no colors in there, but there's going to be a first release. There's still, each vintage, there's the final data is, the final point or final observation is preliminary. That's the advanced estimate. That's not fully observed. If this data had only regular revisions, then all we would have is orange along the main diagonal. Because now this revision takes place only every 4 quarters, it's an annual revision, what this means is that you get this first release for observation R, but it remains as preliminary up to the quarter R plus 4 when it becomes final. So the blue guys appear. Okay. Why would this have an impact on what I've said before? In particular, why is it that the function f, whose stationarity I assumed so far, will no longer be stationary? Well, the reason is the following. It really actually depends on the predictors, on the model you're using to forecast. So suppose that you're at time r, and you're forecasting the observation at time r plus 1. So suppose that you're using these data to forecast the final value, yr plus 1. Now suppose that you're using an AR1 model and you want to test whether that AR1 model has a 0 mean forecast error. If you're using an AR1 model, the predictor for R plus 1 is going to be the last observation here, which is preliminary. You go one step ahead and now you're at time R plus 1 using this vintage of data to forecast YR plus 2. Well, because you're using an AR1 model, the predictor is still going to be the last point here, which is a preliminary value. So, if we were to use an AR1 model in this example, even though there's the blue guys there, actually they wouldn't enter the problem. Asymptotically, all it matters is the orange guys. But now suppose you have an AR2 in mind. If you're again at time R trying to forecast YR plus 1, well, if you use an AR2, now the predictors would be a preliminary value and a final value. Those would be your XT. But if you go one step ahead, you're now at R plus 1 trying to forecast what happens at R plus 2, now your predictors become preliminary because they would be the last 2 points. So same thing if you were at R plus 2 trying to forecast what is happening at R plus 3, the predictors would be preliminary. Same here, but once you reach an annual revision period, now the predictors would be a mix of preliminary and final. So what this exercise explains or suggests is that the structure of the predictors is going to change with the time period t at which you forecast. Once you allow for annual revisions, these predictors can change depending on how long your autoregression model is. And so assuming that the function f is stationary is not a good idea because the predictors are now changing over time. So that is why the stationarity assumption is not a good assumption. And so here's the example that I was explaining. You have an AR1 or an AR2. It's clear that that introduces some periodicity. That was the interesting part in this project, is that, as I've suggested, now the structure of the predictors in this simple example is going to alternate between a preliminary or a final value, depending on whether you have an annual revision or not. And so that means the structural, the functional form of the testing function is periodic. And periodicity is a form of time heterogeneity that is not compatible with stationarity. And so what do we do in the paper? We change the assumptions from West and Clark and McCracken to allow for this periodicity, right? And so in particular, and that's again why the notation becomes ugly, now I have introduced lambda. Lambda here is the periodicity. So in my tables before, I was thinking about quarterly data, so lambda was 4. But if you had monthly data, you'd have 12. Right? And if lambda is equal to 1, then you don't have annual revisions. So what we're doing is creating a function, testing function that can take up to lambda versions depending on this form of the predictors, and then we're collecting all those versions of f and the derivatives into a vector v, and then we're going to assume that the G function composed of these objects is stationary. And so through that, what we can show is that the statistic that is computed normally under no revisions or no annual revisions can again be decomposed in this particular manner. And what changes here is that S1 is still an average of the testing function, but importantly now this testing function is periodic, is no longer stationary. The other main change is that, remember this second term here captured the estimation uncertainty, and before I had F, capital F. That was because capital F was the expectation of the derivative of little f, and that was time stationary, so there was no t involved. But now that I allow for no stationarity, for heterogeneity, now the estimation uncertainty affects the statistic through the average of the different function forms of f. And so f bar appears rather than f. And what we show in the paper is that in the end, everything works out. You end up with the same sort of variance that is quite complicated. With the difference is that the terms in red, they're different. Not only is f bar appearing rather than f, but these omega 1 and omega 1, 2, now they're variances that pertain to heterogeneous arrays rather than stationary data. And so I might be out of time, but essentially the main reason why these things work out, why can I use Clark and McCracken? Well, what they do is they estimate these objects using hack estimators. And the result that might not be well known by everybody, but I certainly know it well because that was the topic of my thesis many years ago, is that you can use these so-called kernel-based estimators or hack estimators without assuming stationarity. So they are still consistent under heterogeneity. And that was a really nice surprise because that means that one can use the standard estimators under different assumptions, and that's how we justify the Clark and McCracken approach in these these richer contexts where we are allowing for annual revisions. I'm out of time, I suppose. So I'll show you maybe I show you some simulations. 1 or 2 minutes. Okay, so here's this, I'll end with this table. What I have here is a set of results, both size and power, for testing zero mean prediction errors based on an AR1 or an AR2 model. And so that's what distinguishes these two sets of rows. And there's different statistics here, test statistics. One is the Diebold and Mariano. This is the most famous one that everybody knows, where you don't allow for estimation uncertainty. So it's just the average of the statistic F. And the Clark and McCracken is the one that I've described, using normal critical values with that complicated estimator for the variance. And then we have two bootstrap methods, 1 and 2. One is the one that would put only the oranges as orange and everything else as final. That clearly is correct if there's only regular revisions. But in my table, I showed you there were all these blues. And so that bootstrap will not be valid unless there's only regular revisions, which happens when lambda is equal to 1. So the bootstrap 2 is the one that I described before. So what you see here is, in terms of size, if you're using an AR1 model, so different lambdas, only when lambda is 4 or 12 do I have annual revisions. When lambda is 1, no annual revisions. So what we see here is that, well, the first set of results shows that there are size distortions associated to Diebold and Mariano. That's because that test does not allow for parameter estimation uncertainty. And second, you see that the bootstrap methods behave very similarly to the Clark and McCracken method, which should be the case in this scenario. And they all do quite well. They're slightly oversized here when lambda is 12, but other than that, they're doing fine. When you're using an AR2 model, that's when you start seeing differences between the bootstrap 1 and the bootstrap 2, because if lambda is greater than 1, you have annual revisions, and as I explained, with an AR2, you now have this periodicity in the function f, which is not captured by bootstrap 1. So what you see here is that the Clark and McCracken is doing quite well, and that at first was surprising to us because we thought that that method was not robust to annual revisions. But then we wrote a paper to explain this. And second, the bootstrap 2, which is the method we studied before only under regular revisions, turns out to be actually very well behaved and is similar to the Clark and McCracken, as it should, because it's mimicking exactly what Clark and McCracken are doing. And so I think I can stop there. That's the main idea. The main idea was to propose a bootstrap method that handles these different data structures, data revision structures. We've accomplished that with this sophisticated application of the block bootstrap, and it turns out that it's actually more robust than we thought it would be at first. Thank you very much.